Hello, I'm Subhashni, working as Assistant Professor at Mallareddy Engineering College for Women. Today, I would like to explain about the optoelectronics. Now, under the heading of optoelectronics, the contents are carrier generation mechanisms, carrier recombination mechanisms, LED, solar cell, PIN diode, and avalanche photodiode. So we'll discuss them one by one. The first is the carrier generation mechanisms. So we have here different carrier generation mechanisms. Now, before we learn about the carrier generation mechanisms, what is carrier generation? So carrier generation is a process in which an electron hole pair is created. So for the creation of electron hole pair, we have different mechanisms. So we'll be discussing here the different mechanisms. So one of them is the carrier generation due to light absorption. So here we can see in the diagram, we have the valence band at the bottom and conduction band at the top. So here one electron is going to move. Now this is the electron indicated with a circle written as E here. So this electron, it is going to move from the valence band into the conduction band by absorbing some energy. So whenever an electron is moving from valence band into the conduction band, a hole is formed in the valence band. That is a deficiency of the electron, which is called as a hole. A hole is created in the valence band, and the electron will be moving into the conduction band. So there will be an electron and hole pair created here in this process. So this electron hole pair is created by the absorption of energy of the photon. So here, for the creation of electron hole pair, this energy should be equal to the difference between the energy gap between the conduction band and the valence band. So an electron hole pair will be created by absorbing a photon of energy equal to the distance between the conduction band and the valence band, which we call it as a forbidden energy gap. So this is the generation of electron hole pair due to light absorption. So we can see here in this diagram, a photon is being absorbed and E photon is the energy of the photon and Eg is the forbidden energy gap. So photon energy should be greater than the energy gap. So if it is greater, that energy will be taken up by electron, which will be there in the valence band. It will be moving into the conduction band. So corresponding to one electron here, a hole is created in the valence band. So we get one electron hole pair by the absorption of a photon, light energy. So this is generation due to light absorption. The second mechanism is the carrier generation or the ionization due to high energy beam. Now in this mechanism, now a high energy beam, which is consisting of highly charged particles, a high energy beam consisting of charged particles, that is the energy of this high energy beam will be much greater than the energy gap between the valence band and the conduction band. So in this process, because the energy of this charged particles is much higher than the energy gap between the valence band and the conduction band, a more number of multiple electron hole pairs will be formed here in this process. Now, as the energy is being utilized for the electron hole pair creation, gradually the energy of this beam will be reducing, and eventually this particle, high energy particle, will be coming to a stop. So this is the ionization due to high energy beam. The next one is the impact ionization. Now in this impact ionization, an electron which is having much larger than the conduction band energy, that is going to give its energy to one electron to create one electron hole pair. So in this process, we'll be having two electrons created, and these two electrons will be responsible for the creation of 4 more electrons. So the process continues like this, and it's an avalanche process. The process is called as avalanche process. Now here we can see one electron hole pair is created, and since the electron is having excess of energy, that is as it is moving along as it is moving along the semiconductor, it is going to give some of its energy for the creation of electron hole pair. So likewise, 2 electrons will be responsible for creation of 4 electrons, and these 4 electrons will be responsible for the creation of 8 electrons, and so on, and the process continues. So this process is called as the avalanche process, avalanche multiplication. So this is about the carrier generation mechanism. The next one is the carrier recombination mechanisms. So carrier recombination is a process in which an electron is going to combine with a hole. So in this process, when an electron is combining with a hole, an amount of energy is being released in this process. So if the energy is in the form of photons, then it is called as a radiative recombination. And if the energy released is in the form of phonons, that is heat energy or phonons, then the recombination process is called as non-radiative recombination process. Now coming to the radiative recombination process, we are discussing about the recombination processes. The first one is the band-to-band recombination process. Now we can see the diagram here, band-to-band recombination process. In this band-to-band recombination process, an electron which is there in the conduction band, it will be falling into the valence band, and it is going to recombine with a hole in the valence band. So during this process of recombination, an energy will be released. So this is called as band-to-band recombination process. Then the second one is a trap-assisted recombination or Shockley-Reed-Hall recombination. Now this is the second mechanism, that is trap-assisted recombination. In this trap-assisted recombination process, the electron which is coming from the conduction band, it is going to fall into a trap, that is an intermediate energy level, which will be present because of some defects in the crystal. So because of the structural defect, some traps will be formed in the crystal, and this electron which is coming from the conduction band, that will be falling into the trap. That is in the first process, it is going to fall in the trap. And in the second process, it is going to combine with a hole in the valence band. So this is called as trap-assisted recombination. That is, electron, instead of directly falling into the valence band and recombining with a hole, it will be falling into a trap. So it is assisted by a trap, and then recombination will be taking place. Hence, it is also called as Shockley-Reed-Hall recombination. So this is about the Shockley-Reed-Hall recombination. And the third process is the Auger recombination. In this Auger recombination, now we can see here Auger recombination process. In this recombination process, whatever energy is released in the recombination process, whatever energy is released, that energy will be given off to one more energy or other particles in the crystal. So this process is called as a Auger recombination mechanism. So this is about the carrier recombination mechanisms. Next, we'll be discussing here about the optoelectronic devices. So optoelectronics is a combination of two words. One is optics, the other one is electronics. So here we are going to study about the conversion of light energy into electrical energy and electrical energy into light energy. So there are some devices which are going to convert this light energy to electrical energy and electrical energy into light energy. So we are going to study about those devices, which we call it as the optoelectronic devices. So the first one in this optoelectronic devices is the LED, that is light emitting diode. So coming to the light emitting diode, the principle behind the working of this LED is electroluminescence. So what is electroluminescence? So electroluminescence, it is a property of the material of to convert an electrical energy into light energy. So here LED is doing the work of converting an electrical energy into light energy. So here we can see the symbol of this LED. Now this is the symbol of diode, LED, light emitting diode. So we have the same as the symbol of the PN, ordinary PN junction diode. And extra we are going to have two arrows above this symbol, indicating that in this LED, in this diode, light will be emitted. To show the light is to show that light is being emitted, we are going to indicate by arrows here. So this is how practical LEDs look like, and we have different colors of LEDs here. You can see here different colors of LEDs here. So here we have two terminals for the LED. One is shown as a longer lead, the other one is shown as a shorter lead. So the longer lead is going to indicate that it is the positive terminal, and the shorter lead is going to indicate that it is the negative terminal. So this is how the practical LEDs look like. Now coming to the construction of LED. So here we'll be having an PN junction diode. So for the construction of LEDs, we are going to take direct bandgap semiconductors. So using those direct bandgap semiconductors, we are going to construct the LEDs here. So we can see here in this constructional diagram, we have the P-type material and an active region and an N-type material. So active region is the region from where we are going to get the light. So light is emitted from this particular active region. So here we are going to take one N-type material above which we are going to have the active region, or it is also the depletion region, and above that we are going to have the P-type material. So this is how the construction looks like. Now we can see in this diagram, now here we have the P-type material, and at the bottom we are going to have the N-type material. And here for metal, contacts, we are going to have metal film connections here, and light is emitted from this. That is, it is being emitted from the active medium, which is shown with red color arrows here. And we can see here the carrier recombination process is taking place. We have the hole in the valence band, that is in the P-type material, we are having the holes indicated by the circles. And in the N-type material, we are going to have the electrons indicated by these black colored circles. So the electron is moving from N-type material into the P-type material, and recombination will be taking place at the junction. And from that active medium, we are going to have the light emitted. So we have seen already in the previous topic that whenever carrier recombination mechanism is taking place, energy will be released in case of radiative recombination. So here energy is released in the form of photons, that is in the form of light energy is being released. Now here we can see we have the P-type material. This is the P-type material combined with an N-type material, forming a PN junction diode, and it is connected in the forward bias. That is, we are connecting the P-type of the semiconductor to the positive terminal of the battery, and the N-type of the semiconductor is connected to the negative terminal of the battery. So whenever we are forward biasing this P-type PN junction diode, the positive terminal is going to repel the holes in the P-type, and the negative terminal is going to repel the electrons in the N-type. So the electrons from N-type will be moving towards the junction, and the holes from the p-type will be moving towards the junction, and the recombination will be taking place. You can see here the recombination taking place. So whenever the recombination takes place, energy will be released. That is, energy is released in the form of photons here. Now you can see the energy level diagram here. We have the conduction band of the n-type, we have the valence band of the n-type, and this is the conduction band of the p-type, and this is the valence band of the p-type. Now we can see the Fermi level here for the n-type, and for the p-type the Fermi level closer to the valence band. So here, because of the forward bias, the holes, the electrons from the n-type, they will be pushed into this region, that is the active region, or this is the depletion region, and the electrons will be combining with the holes in the depletion region. So by this recombination, light is going to be emitted. So this is about the working of an LED. So this is the explanation for the working of the LED. Now coming to the VI characteristics of LED. So we are going to take the forward voltage along the x-axis and the current along the y-axis we are taking. And as we have already seen that practically available LEDs will be of different colors. So here we have drawn the VI characteristics for different colors, different wavelengths we can say. So now if you are taking, for example, if I take the green color LED, now as the voltage is increasing, the current will not increase initially, but after a particular voltage, the current starts increasing rapidly like this. So this particular voltage from where the current starts increasing, that particular voltage will be calling it as the knee voltage. So you can observe here, each color is going to have a knee voltage, a particular knee voltage. Each color is going to have different knee voltage. So here you can see for red color, they have given this voltage. So for different colors, we are going to have different knee voltages here. Now, as the voltage is increased, the current will be increasing. Now, as the current is going to increase through the diode, the brightness of the light is also going to increase. That is, the intensity of the light will be increasing as we are increasing the voltage. So you can control the brightness of the light by varying the current here. So next, coming to the advantages of LED. Now LEDs, they have very fast switching times which are of the order of nanoseconds. And LEDs, they are going to consume low power. They will be having better controlling. That is, we can control the brightness or the intensity of the light by controlling the current. By controlling the current which is passing through the LED, we can control the intensity of the light. Then they are economical and they are also reliable. They are available at low cost. So, and also their size is very small. So obviously they are portable. And the efficiency of LED is very much higher. Now coming to the disadvantages of LED, the first disadvantage is overcurrent or the over voltage. So if the current is increasing beyond the limit, the LEDs will be getting damaged. That is because of the overcurrent, the LED is getting damaged. And overheating due to radiant power. That is because of excess of increase in the radiant power, it gets overheated. So as the temperature is increasing, it gets overheated and it will lead to the damage of the diode. So these are the advantages and disadvantages of LED. Next, applications of LED. We can use LEDs as an indicator in the circuits, and we can use as display panel in the indicators. Like you can see here, the 7-segment display format, which we'll be finding at different display units at, say for example, we can see at railway stations for the display of the timings, display of the stations, we'll be seeing this kind of 7-segment displays. Then we can find them in digital watches, and calculators, and also in multimeters. And we can also use them in remote control systems and also in burglar alarm systems. So this is about the LED, the principle, the construction, the working of an LED, the advantages and disadvantages of LED, and the applications of LED.